Electronic system design, examples of system design. And the big question is whether it's a system or a component. In this lecture, we're going to look at the secret of good system design. First of all, we're going to look at how to understand the application, what the customer or user is trying to do, where is the customer or user trying to do it, and what is the accuracy or precision of the units required. Is it 10 seconds, 1 volt, 10 microamps, 10 picoseconds? We need to understand that to do good system design. We're going to take a holistic view of the problem. We're not going to rush into a solution. We're going to spend some time understanding the customer's problem and the customer's application. And then we're going to try and consider several different approaches to the same problem. There may be one that's beneficial over another. It may be cheaper, it may be more efficient. And finally, we're going to approach the problem systematically. We're going to use a concept called the V model, and I encourage you all to document your decisions. In many system design problems I've done, when you're halfway through the design, you will discover you're wrong, and you can now change the decision and try again. And throughout your system design, you must also always consider how you will validate and verify the results. And we'll talk a little bit more about that later. In system design, we all start with the same basic parts. The difference between good system design and bad system design is how we use the parts to meet the customer need. It's very easy to use the latest processor or the most fancy screen, but actually it's important to understand what the customer wants to do with the product, not what you want to put into the product that's important. In electronic system design, it's the connections between the blocks that are actually the key to good system design. And I've shown a very typical system design here, which could explain many different things. It could be a radio receiver. It could be a new form of wireless communication. It could be a sensor detecting the weight of a new train. But these 5 blocks are generally all that involved in system design. The starting source is the signal source. The signal may be a voltage, a current. It could be a change of voltage or current. It could be a resistance. And the key question here is what specification describes the input signal? What do you need to know about it to do your design? Once you understand a little of the signal source, you then look at the signal conditioning. Do you need to amplify or attenuate if the signal is too large? Do you need to filter it? Do you need to shape it? Do you need to change the frequency of the signal? Perhaps you're receiving it at very high radio frequency and you want to shift it down to do baseband processing. Do you need to limit the signal? Do you need to make sure that it doesn't overload and damage the following parts? The third part is perform the operation. And this could be done analog or digitally. But in modern technologies, most of the applications use a digital processor. We've got a question of what specification, accuracy and precision again is needed for that digital processor. Once you perform the operation, once you've done to the signal what you require to do, perhaps detect a level, amplify it, convert it into something more suitable, you need to pass it to an output driver or an output conditioner. If it's a digital processor, the output will be in digital form. But if you're driving analog loudspeakers, then you need to convert it into something that's more suitable. And the output driver has to interface with the operations and also prepare the signal for passing to the output stage or the actuator. And the output stage is not necessarily an electronic product. It could be a piece of hydraulics to operate the brakes on an electric locomotive. It could be a loudspeaker. It could be a vibration table. It could even be an entire engine. You need to understand what the specification is and how you're going to apply that. A good system engineer not only knows the blocks, but they also know the interfaces and how the interfaces will connect together. Many failures I have seen in student projects and also in commercial projects is when the individuals were too focused on the internal block function and didn't consider how that internal block function was going to connect to other parts of the system. I want to talk now briefly about an analog system that I was involved with. Here we see a typical analog system, and in its day it was one of the most complex analog systems ever developed. It consisted of 3 parts, which contained many amplifiers, control functions, most of which were implemented in the analog domain. Today, you would put in a processor, but when this was developed, it was all done in analog. And this is a simplified block diagram. It's called a telephone subscriber line interface circuit. It connects old-fashioned hardwired telephones to the network. And I said it has relevance to China. I and my company sold millions into China in the 1990s to connect telephones to the telephony network. This was before mobile phones existed. And these systems went into a building called a central office, sometimes called a telephone exchange. And every city had a central office and connect up to anything up to 3 million lines. In this system, it consists of roughly 3 parts. There's a high voltage analog part, a low voltage analog part, and a low voltage digital part. And my role in the system was to look after the high voltage analog part, which ran from 48 to 55 volts, but also had to deal with things like lightning strikes and people connecting the power grid onto the network. These in turn were integrated into circuit boards. And here we see a typical 16-channel circuit board containing many of the analog systems into a super system. In turn, these boards were assembled into an entire telephone switch, which contained many boards, and a large telephone switch could accommodate anything up to 3 million lines. And there were several of these developed in China. A city such as Chengdu today would have several large switch stations all connected to the digital network. Remember, mobile telephony did not exist. If we look at the future plans for the next generation China network, we see there is a ring consisting of main cities that contain the core of the network, and they have sub-switches that connect out into the regions of the network. Key point here is, although I consider the 3 integrated circuits as a system, it just becomes a component into the greater network to build the boards, to build the switches, and the switches generate the whole communication system that's planned out for China. So in some cases, one person's system is often another person's component. Now I've got a class exercise for you. Split yourselves into groups of 4 and discuss whether the following are systems or components. I'll give you 10 minutes to think about that, and then we'll continue with the rest of the lecture. Thank you.